Hi, welcome back to our lecture series on physics. This is our fourth video of the series. In the first one, we spoke about electromagnetism. In the second, we discussed the force experienced by a conductor, a current carrying conductor, when placed in an external magnetic field. In the third video, we discussed the functioning of electric motors, the principle on which they work, and the many applications of electric motors. So let's use all of that knowledge in today's test. So there are going to be a series of questions which will test the conceptual understanding on everything that we have discussed so far. So let's do a quick summary on what we did in the last class on electric motors and then get to the test. An electric motor is a device which converts electrical energy into mechanical energy. I demonstrated different kinds of simple motors that we can build in no time at all. Some of the demonstrations are quite beautiful. The principle of an electric motor is that a current carrying coil is placed in an external magnetic field. It experiences a force, a torque, as a matter of fact, and then it starts to rotate. And then we spoke about the many applications of electric motors. So based on everything that's been said so far, here is the test. Let's look at a few practice questions. An electric charge Q moving in a straight line enters a uniform magnetic field, which is directed into the plane of the screen and moves as illustrated. What kind of charge is Q? Right? And there are four options provided. Now, this is a simple application of the left-hand rule. So clearly, if you imagine the three fingers of your left hand, the middle finger, the index finger, and the thumb held perpendicular to each other, the index finger pointing into the plane of the screen, that is the magnetic field. The electric charge is moving from left to right, so your middle finger points in that direction. Your thumb will point in the upward direction, which indicates that a positive charge would experience a force in that direction. If a positive charge plus Q were moving into the electric field in this direction, then the force would be acting in that direction. But it isn't. It's acting in the opposite direction, which essentially means that this is a negative electric charge. And that is the answer to this question. This is an application of Fleming's left-hand rule. The next question. A wire AB carrying a current is placed in a magnetic field. The force exerted on the wire can be zero because of the following. Now, which of the following reasons makes the force exerted on the wire zero? Let's look at the options. The wire is perpendicular to the magnetic field. The wire is parallel to the magnetic field. The magnets are weak. It is not possible for the force to be zero. Now, if you recall the formula which is used to write the magnitude of the force experienced by a straight current carrying conductor in an external magnetic field, it is B I L sine theta. So B is the strength of the magnetic field, I is the current here. This is the current in the conductor. L is the length of the conductor, which happens to be in the magnetic field. And theta is the angle between the magnetic field and the conductor. Now, when the wire is perpendicular to the magnetic field, sine theta becomes 1. That is when the force is the highest. When the wire is parallel to the magnetic field, the angle theta is 0, sine theta becomes 0, and therefore the force between the force exerted on the conductor is 0. So that is the answer to this question. When the wire is placed parallel to the magnetic field, the force exerted by the external magnetic field on the current carrying conductor is 0. The next question: which of these is a valid difference between a permanent magnet and an electromagnet? Permanent magnet has a magnetic field around it, but an electromagnet does not. Clearly, that is not the right answer, because both magnets have very similar looking magnetic fields. The second option is permanent magnet has north and south poles, but an electromagnet does not. That also is not true. In fact, in an earlier video, I showed you a simple demonstration that established that electromagnets also have north and south poles. So B is not the right option either. A freely suspended permanent magnet points in the north-south direction, but an electromagnet does not. That also is not correct. For all practical purposes, an electromagnet is a magnet, and all properties of permanent magnets will be seen in electromagnets as well. The last option is the polarity of an electromagnet can be reversed. It's not possible in a permanent magnet. That is the right option, because by simply reversing the direction of the current flow, the polarity, the north and south poles of an electromagnet, can be reversed. So D would be the right option. Question number 4. By what means can we make an electromagnet stronger? Option A is increasing the magnitude of the current which is flowing. Remember, there is a current that needs to flow in the coil for it to become a magnet. So is it by increasing the magnitude of the current? Is it by increasing the number of turns in the solenoid? Is it both A and B, or is it not possible to make an electromagnet stronger? The answer is C. There are multiple ways in which an electromagnet could be made stronger. One is to increase the magnitude of the current flowing through it, and another way is to increase the number of turns. What does it mean when we say number of turns? So the number of coils. So we could say that this is a coil with 1, 2, 3, 4 turns, and this is a coil with 8 turns. And the number of turns of the coil will determine the strength of the electromagnet. So the option is C. Next question. Describe in detail the motion, and this is not a multiple choice question. Describe in detail the motion of a charged particle Q. It's a positive charge Q with of mass m, when it enters a uniform magnetic field which is directed into the plane of the paper. So this is an application of Fleming's left-hand rule. And once we apply it, then we have to recall some principles from rotational motion to explain the movement of the charged particle in some detail. So what happens when a charged particle Q is moving in that direction? So let's apply Fleming's left-hand rule. Remember, this is a positive charge. So the direction of the index finger, which points in the direction of the magnetic field, should be into the plane of the screen, because that's the magnetic field. The middle finger points in the direction of the velocity of the moving charge, and then the thumb will give you the direction of the force which acts on it. So this is our positive charge. And by using Fleming's left-hand rule, we have determined that the direction of the force is downward. This is simply by using our three-fingered left-hand rule. So because there is a force in the downward direction, there is an acceleration in the downward direction. And let's imagine it goes here. And if you apply Fleming's left-hand rule again, at this stage, the charged particle is moving in that direction. And you apply Fleming's left-hand rule once again, and you will see that the force is acting that way. And then the charged particle moves here. And when it is there, the velocity, instantaneous velocity of the charged particle is like that. Once again, you apply Fleming's left-hand rule, and you will see that the force is acting in that direction. So at all points in our analysis, we have found that the force is perpendicular to the instantaneous velocity of the charged particle. So what I have described here is the force exerted on the charged particle, because it is always perpendicular to the velocity, acts like the centripetal force on the charge Q. And because it is a centripetal force, the charge begins to execute circular motion. As long as the charge is inside the magnetic field, it executes circular motion. It is because the force is at all points perpendicular to the direction of the velocity. So let's calculate the magnitude of the force. So we know that the force on a current carrying conductor is BIL sine theta. Now there are a few simplifications we can have here. Theta is 90 because the charged particle has entered the magnetic field at right angles to it. Therefore, sine theta is 1. So we have simplified this to this. Then what? We know that the current I is simply a measure of the amount of charge that flows through the conductor in unit time, the number of coulombs of electric charge per second. So if we were to replace I by Q by T, you have now consider L by T. You can think of this as the distance traveled by the charged particle in time t, which essentially is the velocity, the magnitude of the velocity of the charged particle. By substituting L by T by V, we have where B is the strength of the magnetic field, Q is the electric charge, and V is the velocity, the magnitude of the velocity. Now this force which is acting on the body essentially is the centripetal force. So we can say that the centripetal force on the charged particle is equal to so we have, by cancelling one of the V's, we have MP. So what we have determined is that one, the force that acts on the charged particle is always perpendicular to its instantaneous velocity. It acts as the centripetal force. The charged particle begins to describe a circular motion when inside the magnetic field, and the radius of this circular path is given by this expression. So this r is the radius right? So this is the expression that we have derived. Let's see what actually happens in this illustration. You can see that the force at all times when the charged particle here is here, the force is in this direction. When the charged particle here, the force is in that direction. When the charged particle here, the force is in that direction. The force is always equal, but directed towards a center which is around here, and therefore it is circular motion. So this is a description of the motion of the charged particle when inside the magnetic field. When it is outside the magnetic field, when it is here or here, notice that there is no external force acting on it, and therefore a body has to continue in a straight line path because there is no external force. But when inside the magnetic field, it does experience an external force and executes circular motion. So that is the answer to the question. Let's come to a similar question, but this one involves an electric field. Now this is a uniform electric field in the upward direction, and much like before, a charge, positive charge Q, enters it from the left hand side, moving at a constant velocity v. It enters the electric field. Describe the motion of the electric charge. Now, a problem like this, together with the earlier problem, will illustrate how electric fields and magnetic fields behave differently when it comes to a moving charged particle. So let's analyze the situation. So we have a charged particle which is moving at constant velocity v, and clearly so this is the initial situation. Let me describe it here. There is a horizontal velocity v, and the vertical component of the velocity is 0 because it is not moving in the vertical direction at all. It's moving in the horizontal direction. When it enters the electric field, it experiences a force Remember, this is a positive charge Q. So the force experienced by it in the electric field is QE. So suddenly, when it enters the electric field, it starts to experience the force. So what is the acceleration of the charged particle? The acceleration of the charged particle, A, is force by mass, that is QE by M. Now the important thing here is, and again we go back to Newton's laws, there is a force exerted in the upward direction because the electric field is in the upward direction. There is no other force acting on it. So the only acceleration it will experience is in the upward direction, because acceleration is always in the direction of the force acting on it. So acceleration also is upward. This also means that the horizontal velocity will not change at all because there is no horizontal force. The only force acting on it is in the vertical direction. So the only acceleration it experiences is in the vertical direction. So what happens is, if you analyze its motion in the vertical direction, we can use this equation, which is S is equal to ut plus at square by 2. S is equal to initial velocity in the vertical direction is 0, plus acceleration is given by this expression here. So since Q, E and M are constants, they are not changing, we can simply call QE by 2M as some constant K. So we have the expression S is equal to KT square. This implies that the body begins to move in a parabolic path. This is a quadratic equation between S and time. So in the final analysis, the horizontal velocity never changes, but the vertical velocity changes because there is a vertical acceleration which is equal to QE by M. Therefore, it describes a parabolic path. So if you go back to our picture here, it would be something like this. In fact, this should remind you of the parabolic path of a body which has been thrown. It executes a parabolic path on its way back down to earth because there is a force acting in the vertically downward direction. This is just a force acting in the vertically upward direction, but the analysis is much the same. The horizontal velocity does not change, the vertical velocity changes. So it's very much like projectile motion, except that the force is acting in the upward direction rather than in the downward direction. An alpha particle moving towards the east is deflected towards north by a magnetic field. What will be the direction of the magnetic field? So an alpha particle, just to remind you, an alpha particle consists of 2 neutrons and 2 protons. So it's got a plus 2e charge to it. It's a positively charged particle. It is moving, so the alpha particle is moving east and it is deflected north by a magnetic field. If it is deflected north, the force must be acting in the north direction. So the force exerted north direction. Having determined that, we simply apply Fleming's left-hand rule with the middle finger in the direction of the motion of the particle, which is to the east, the force, the thumb, in the upward direction, and your index finger will be pointing into the surface of the screen. So the magnetic field as given by Fleming's left-hand rule is into the plane of the screen. Next question is, why does Earth have a magnetic field? Now, we all know that Earth has a magnetic field. In fact, when in class 6 or 7, when we talk about compasses, we learn that a compass always comes to rest in the north-south direction, or any magnet, when freely suspended, comes to rest in the north-south direction because of Earth's magnetic field. Now, the question is, why does Earth have a magnetic field? For that, we have to understand the interior of the Earth. Now, of course, we are on the upper crust, but inside that is the mantle, the outer core, and the inner core. The inner core is under immense pressure and is a solid part of the interior of Earth. But the outer core is liquid. It is under tremendous pressure and has extremely high temperatures. Because of that, there are two things that happen. One is, there are charged particles in the outer core. It is the immense pressure and the high temperatures that cause the atoms in that part to be electrically charged. And because of the liquid nature, the physical nature of the outer core is liquid, there are convection currents. The convection currents essentially mean that there is movement of this liquid. So imagine the charged particles moving around because of these convection currents. So what we are talking about is the continuous flow of charged particles. Of course, that is another way of saying that there is an electric current inside the outer core of the Earth. And we all know that any electric current will have a magnetic field around it. So that is the description, or that is the explanation for Earth's magnetic field. So you can call Earth a giant electromagnet. In fact, some questions for you to think about. If the moon does not have a magnetic field, if Mars does not have a magnetic field, then what can you conclude about the interior of these planets? But that's a question for you to think about. Our last question in our practice session is, we have a schematic diagram of the motor and we have to determine the direction of rotation of the coil. So let's analyze this. What rule do we use? We use Fleming's left-hand rule, like we have done on so many occasions. So let's first write down the direction of the external magnetic field. The magnetic field is from the north to south pole. The current flow is as indicated here. The current is flowing in that direction over there and in that direction over here. So a simple application of Fleming's left-hand rule tells us that there is a force acting in the downward direction on this part of the coil, and an equal force but in the upward direction on this part of the coil. So when on a coil there is an upward force in that direction and a downward force in that direction, it essentially causes a rotational motion. So we can conclude from this analysis that it rotates in the anti-clockwise direction. Well, that was just a few sample questions that we analyzed to test the conceptual understanding of all the topics we have covered so far. I hope you got a good understanding of everything we discussed. There are many more questions on our website. Thanks for watching.